The purpose of this lab is to determine the sign of a charge of a common object. You can use the equations we've learned in class to determine the excess charge on an object. This is possible because we know the tendencies of certain types of materials. And now for the experiment. For the data, my U-tape was 8 inches long, which converts to 0.2032 meters. The tape had a density of 1 gram per meter, so the mass of my U-tape was exactly 0.0002032 kilograms. Part 1 of this lab involved observing the interaction between the U-tape and other common objects. I began by charging the tape per the instructions in the lab manual. I then held the tape up to other common objects to observe the interactions it had. The first interaction I observed was between the tape and my hand. I observed a slight attraction. The next interaction I observed was between a piece of tape and a neutral ruler. Here I also observed a slight attraction. The next interaction was between the tape and a charged pen. Running the plastic pen through my hair gave it a negative charge, and when I put it up to the U-tape, I saw a strong repulsion. Finally, I made another piece of U-tape and held both pieces up to each other, and I saw that there was a strong repulsion. This makes sense as they were charged the same way and should have the same sign on their charge. Now to determine the excess charge on one of these pieces of tape. This diagram is from the lab manual and indicates how to set up the experiment, with one piece of tape loosely placed over two supports, to allow for movement due to repulsion from another piece of tape, which I stabilized with my hands through the experiment. And now for the data from the tape-to-tape experiment. So the separation before movement was 0.03 meters between the tapes. The displacement of the tape after movement was 0.01 meters. To answer one of the questions from the lab manual, since the momentum of tape B is not changing, the net Y component of the force on tape B is constant. The objects in the surroundings that exert a vertical force on a floating portion of tape B are the Earth in the form of the gravitational force and the electric force from the other piece of tape pushing it up. I've made a free body diagram to depict these vertical forces on the floating portion of the upper piece of tape. Tape B. Force pointing upward is the electric force on the floating portion of tape B exerted by the lower tape. The force pointing downward is the gravitational force provided by Earth. It's calculated by multiplying mass and gravity. Logically, we know that in order to cause the upper piece of tape to float upwards, the upward electric force must be at least equal to the gravitational force. Through this realization, we can come up with a formula for the charge required on the piece of tape, for tape B to float above tape A. By setting the equation of the magnitude of the electric force equal to the magnitude of the gravitational force, we get this. For this lab, we can make the assumption that the two pieces of tape have the same charge Q because they were charged using the same method. Once the equation is further simplified, we can get that the magnitude of the charge Q on one of the pieces of tape equals the square root of mass times gravity times 4 pi epsilon naught times the magnitude of the distance squared. The next step is to plug in all of the values that we have. The mass of the floating piece of tape is 0.0002032 kilograms. Gravity is a constant 9.81 meters per second squared. 4 pi epsilon naught is equal to 1 over 9 times 10 to the 9th coulomb squared over Newton meter squared. The magnitude of r squared is the original separation plus the distance the upper tape floated up squared. This value was equal to 0.0016 meters squared. Plugging all of this into the equation gives us a charge of 1.883 times 10 to the negative 8th coulombs. Now that we have the magnitude of charge for each piece of tape, we can go ahead and calculate the number of excess electrons on a piece of tape through their simple relationship of resultant charge over the charge of one electron equals the number of excess electrons. Performing this calculation gives us 1.175 times 10 to the 11th excess electrons on the piece of tape. To calculate the ratio of excess electrons to atoms, I simply calculated the number of atoms on one side of tape and compared that to the number of excess electrons. In conclusion, this experiment really forced us to utilize our knowledge of the tendencies of attractive and repulsive electric forces. We saw that the tape was negatively charged because it was strongly repelled by the negatively charged plastic pen. We were able to approximate the excess charge on the tape because of our knowledge of gravitational forces, electric forces, and equilibrium. The main random errors were most likely measurement errors, as the distances we measured were very small. It is fairly hard to determine how much the tape floated up, for example. The main systematic errors were most likely due to the charging of the pieces of tape. Different types of clear tape may be more susceptible to accepting electrons than others, and thus the experiment has a large potential to be different from student to student. Using GlowScript, I performed the same calculations and got the same values for the excess charge and the number of electrons on one piece of tape. I modeled each piece of tape as a point charge. The white arrow is the electric force of the lower piece on the upper piece. The magenta arrow is the gravitational force on the upper piece. Thank you for listening to my lab.